The example that we went into with symmetry breaking was for a supercritical pitchfork, and we looked at one of the options, but actually the symmetry could be broken in either direction. So by adding a small second parameter, so okay, let's see, here's the normal form for a pitchfork, a supercritical pitchfork, but if we just add, if we make that h plus rx minus x cubed, this h is just a small shift in where this line is coming through, and that causes the type of symmetry breaking that we explored earlier. And depending on the sign of h, we can end up with either of these scenarios. So in both cases, the pitchfork is broken into a stable state and a saddle node, and it's just a question of which stable state has become the one that we will follow. So in this case, we'll follow the upper branch, and in this case of symmetry breaking, we'll follow the lower branch. The transcritical bifurcation can also be broken by a slight perturbation. So let's say we let x dot equal h plus rx minus x squared. Let's look at how the perturbations change. So I'm going to plot x squared, and then I'm going to plot h plus rx for h positive. And let's say h is now fixed at this positive number, and we're changing r. Note that for all the values of r we try, we still have 2 fixed points, with the exception of when r, in the limit when r becomes infinity, but actually r can never be infinity. So we always have 2 fixed points, and they never collide with each other. So we just always have 2 states, and that bifurcation diagram will look like this. That one will be stable, this one will be unstable, and even as we adjust the slope, both fixed points will always exist. Okay, so that's what happened for h positive. That was, we broke the symmetry of the problem, and that broke the 2 states apart, getting rid of any bifurcations. Now let's think about what happens if we make h negative. Now there are values of h where there's no intersection between our 2 curves, but let's adjust our slope, leaving h fixed. Okay, we're about to go through, we're a saddle node bifurcation, where we have 2 fixed points, and we continue to have 2 fixed points even as r gets quite large, the slope. And if we take r in the other direction and make it negative, we again go through a saddle node bifurcation and have 2 fixed points. So what does that look like? We have a parameter, and for some values of that parameter we have no fixed points, but we have 1 saddle node, and we have a second saddle node. So the symmetry broke here by this piece turning into a single saddle node and this piece turning into a second saddle node. So in this case, if the symmetry breaks in that direction, we continue to have a bifurcation. In fact, we now have 2 bifurcations, and they're both saddle node bifurcations. So what have we noticed when we break the conditions of these very special bifurcations? That would be the pitchfork and the transcritical. We either end up with no bifurcations or we end up with saddle node bifurcations. And so that emphasizes the point that saddle node bifurcations are the type of bifurcation that we're going to see when we're working in a problem with no constraints. I want to go back to the pitchfork and think a little bit more about breaking the symmetry there. And we've thought about what happens if we fix h and then we adjust r. And actually, we've seen at another point in time what happens if we fix r and we adjust h. In that case, we're going to be in the bistability case, where we have one fixed point for some range of h, and then at some point we gain via a saddle node bifurcation 2 more fixed points, and so we have 3 fixed points for a while, and then as h continues to change, at some point we lose 2 of those fixed points through another saddle node, and we're back down to 1 fixed point. While if we change r instead of h, we get these types of pitchfork-like pictures that we've been looking before, and that suggests that we can draw a diagram in 3D that I think you'll probably recognize of what happens to the fixed points as we change both those parameters, as we change both r and h. So there's a region of RH space where we have 3 fixed points, and it's a relatively small region. When h is too large or too small for some value of r, we don't expect to have the 3 fixed points anymore. And then in this particular picture, which we haven't actually thought a ton about, in this particular picture, if r gets too small, then we only have 1 fixed point, only 1 intersection occurs. And so the region of the space where we have 3 fixed points looks like this. So in this region, we'll have 3 fixed points, and everywhere else we expect to have 1 fixed point. And we can try to draw in the surface of the fixed points. Let's see, if we fix h and we're varying r, if we're in exactly the right spot, we have a pitchfork. So that pitchfork is sort of directly overhead this center line. And then if we think about fixing some value of r and changing h, we expect our bistability picture. I suggest actually looking in the book. This picture is going to be horrible again. It's the same cusp-catastrophe picture that I tried to draw the other day, and that I'm just really not very good at drawing. Okay, here I am having tried again. The pitchfork that happens when h is fixed at 0 is right here. So the top branch goes up on this top thing, the middle branch goes across through this center area, and the bottom branch comes down here. And then the bistability that happens when r is fixed and h is varied is right here, and that bistability can of course disappear depending on what value of r we're at. The symmetry breaking in the pitchfork is sort of closely related to the types of models that bring us this bistability.